It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee. Hi guys, welcome to the final video for the first topic of Year 12 Chemistry on monitoring the environment. This is subtopic 1.5, which is all about atomic spectroscopy. Alright, so spectroscopy is a really great, useful technique within chemistry. It's also used quite a lot within physics. So if you're doubling up in physics, you'll probably look at emission spectrums in particular as well. But basically what we've got up here, this is the visible spectrum of light, all right? So Roy-G-Biv, starting from red, going through orange, yellow, green, blue, indigo to violet, okay? And if we're talking about emission, you'll see emission, we're only looking at the certain specific wavelengths of light that's emitted. So you can see these bands here, there's certain bits of light that are emitted. If we're looking at absorption, we're looking at what light is actually absorbed by the species. So you'll see that there's actually gaps in the spectrum now as well. So I'll explain those in a little bit more depth. So the basic principles of spectroscopy revolve around the fact that we have electrons in a fixed energy state around an atom. So if you look at the original model of an atom, you've got like these electrons orbiting around the atom like this. Okay, so you get all these different energy levels of the electrons orbiting around. When they absorb radiation, all right, so light for example, they go to a higher energy level. Right. So if we're looking at atomic absorption spectroscopy, we look at the energy or the that they absorb and going up to that higher energy level. If you're looking at emission spectroscopy, you look at the energy they then give off when they decay back to their original state. They normally give off a photon, which is a form of energy. Now, one of the key things you need to remember is this statement here. You need to learn this, really, really important. Okay, each element can absorb and emit its own unique wavelength of light. And that's really important. So here's an example showing what we're talking about here. So here's the electron in its ground state. It absorbs energy, all right, to jump to an excited state. So if we measure that, that's absorption spectroscopy. What happens? So it doesn't want to stay in that high energy state though. So it will come back down to its normal ground state, and to do that it has to get rid of energy, and it does that by emitting a photon, which we can measure, okay, as visible light. So that's emission spectroscopy. Now, to understand, I guess, these different energy levels, we need to look at electron configuration. Okay, so Schrodinger was a scientist probably most famous for his Schrodinger's cat. And if any of you are a Big Bang Theory fan, you would have obviously heard a lot of stuff in one of the early seasons about Schrodinger's cat and trying to explain about when Leonard and Penny got together. So he had a theory around if you put a cat inside a box with a bottle of poison, all right, that was set to break at an unknown time. At any point within that box, the cat is both alive and dead, and that was Schrodinger's cat symbolization there. So he also did a lot of other things, and one of the things he came up with was that he determined that electrons exist as pairs in orbitals, and they have different shapes. Now, this sort of thing is more very much going on to university level when you're looking at that, so you don't need to worry about it at the moment. But the fact that we have S, P, D, and F orbitals is what we'll look at in Year 12 chemistry. So when you were first introduced to electronic configurations, you probably just looked at how many electrons are in each shell. So here's an example of a calcium atom over here on the right. And we had a look at how many electrons was in that shell, in each electron shell. And we looked at the periodic table. We looked at calcium was in group 2, and it was in period 4. So we knew that because it was in period 4, it had 4 electron shells. Because its atomic number was 20, we knew it had 20 electrons, and we could just go through and use what we call the 2n2 rule to work out how many electrons were in each shell. And we would have written the electron configuration like this: 2, 8, 8, 2. So there's 2 electrons in the first shell, 8 in the second, 8 in the third, and 2 in the last one. Okay. However, Schrodinger has gone through and he's determined that the electrons within those shells actually pair up, okay, and they orbit in different energy levels. And he's used those S, P, D, and F subshells to allow us to work out or have a look at how those electrons are split. So if you're looking at the periodic table, you can the S block of elements here all have the highest subshell of an S block. The P block over here all have a highest subshell of a P block. Same for the transition metals here and the F block. If you need a little bit more explanation around the periodic table and just getting an idea of some of the trends and everything, you can have a look at that video. It's not specifically related to electronic configurations. It's just more so related to the periodic table and the trends in it as well. And I go through S, P, D, and F block in there. So that's something you can have a look at. But if you remember that the S block is over here, the highest subshell they have is the S orbital. That's why they're all grouped together. So in the S block that we're looking at here, it's groups 1 and 2. All right, so they have a maximum of 1 or 2 electrons in their outer shell. Okay, so the highest energy electrons are in the S orbital. All right, similarly for the P block, they have up to between 3 to 8 electrons in their outer shell, and so they will use the P orbitals. And similar for D block, for the transition metals, their highest suborbital is the D one, and they'll have anywhere from 1 to 10 electrons in their suborbital there as well. So when you're writing electronic configurations using subshell notation, this is the little formula you need to use. And the reason I've only got the arrow going there up to 5s2 is because the highest one that you need to know for year 12 chemistry is strontium, all right, which is 38. Okay, so if you go to 5s2, that gets you to the 5th period, the 2nd group, which is strontium, and that's the highest one you need to know. Now, I'm not going to go through this a lot in depth of how to actually write these electron configurations, because if you click on this YouTube video here, that will go through it in more depth. All right, but basically you just follow the arrows through, you fill up the subshells as you go, remembering these rules here, that the S block can, S shell can hold 2, P shell can hold 6, and D shell can hold 10. So just have a look at that video if you need to. All right. There are 2 important exceptions following that, and they are both in the transition metals. The first one is for chromium. Now, if you go through and write out chromium following the normal method that we just had before, you'll end up with 4s2, 3d4. Now, the reason that it doesn't exist as 4s2, 3d4 is because you've actually got a paired set of electrons here. Now, electrons have the same charge, right, and they repel each other. So it's actually much more beneficial for that electron to go into that orbital, the d orbital, and then it be 5 unpaired electrons within that, because within the d orbital there's actually 5 pairs you can have, and the electrons just sit in there individually, so they're not repelling each other, and that's more energetically favorable. That's why it's 4s1, 3d5. For copper with an atomic number of 29, okay, again, if you didn't normally, it'd be 4s2, 3d9. Now, again, it's more energetically favorable for it to have those electrons paired up in the lower energy orbital, which is the 3d, compared to the higher energy orbital 4s. Okay, so you don't have to explain that. You'll probably go through that again first year uni if you go on to do chemistry, which I hope you'll do, because it is the best subject ever. But what you need to remember is that they've both got 4s1 rather than 4s2. If you can remember those, they're probably bound to ask you those at one point. All right, if you're looking at ions, okay, ions are just atoms that have either gained or lost electrons. So all you got to do is follow these steps. Write the normal subshell notation for the atom, work out the charge. If it's positive, take electrons away from the highest subshell. And if it's negative, add electrons to the highest subshell. Again, there's a video on this here under my face. Here, this one here, click on that and you'll get a bit more information as well if you need to. But once you've started getting the hang of a couple of them, you'll find it no problem. So I've done an example here of chlorine, atomic number 17. That's the normal subshell configuration that you've got there. It has a charge of -1, so because it's -1, it's gained an electron. So the 5 gains an electron goes up to 6. You'll notice that this shell now, the 3rd shell, now has 2 plus 6 equals 8 electrons, so it's full. And that's how we do electronic configurations for ions. Zinc, another one there, charge of 2 plus. I've added, now this is important, sorry, I won't jump over this as quickly as I was going to, because it's got a charge of 2 plus, and notice that it's actually the highest subshell electrons that you lose first. So just as back on this one, we put electrons into the highest subshell. In this one, we lose electrons from the highest subshell when we're taking them out. Okay, and then we get a full outer shell down here, and we've got rid of our highest shell. So make sure for transition metals, when you're doing the charge, that you take out the highest subshell ones first. The other thing I'll ask you is to show how the electronic configuration of an atom can help you identify where it is in the periodic table. I'm just going to move my face for a second up to here. All right. So you look at the highest subshell, which in this case is 5. So that highest subshell of 5 tells us it's in period 5. The highest energy suborbital there is the S1. All right, so that's in the S block. If it didn't have this on there, we'd be looking at this one here. All right, and we'd be saying that the highest subshell would be the P, so it'd be in the P block. However, that's not the case. We've got the 5s2. And then we look at how many electrons are in that highest shell. In this case, it's 2 electrons, so it's in group 2. Again, if we had it and we didn't have this, okay, but we had this here, we'd have a look at this one, 6 and 2 together in the high shell, so it'd be in group 8. So that would be the noble gas in that group. Now, I'll just move my face back down here now. All right, so if you've got a handle on writing electron configurations, then we can go ahead to actually looking at emission spectroscopy and absorption spectroscopy. Emission spectroscopy we don't really cover in chemistry because we leave it more to physics. But basically all you've got to understand is that we measure the wavelength of light emitted when that electron decays down to its ground state. All right, and because each element absorbs and emits its own unique wavelength of light, okay, we can determine what that element is from its unique spectrum. So you can see here hydrogen, helium. You can see they've got bands that overlap, okay, but you also see that each of them has a unique band within there that the other one doesn't have. So you can tell what the element is based on its emission spectrum. But what we really are interested in chemistry is atomic absorption spectroscopy, because this not only tells us if we've got something there, but it also tells us how much we've got. So it's kind of a bit of a qualitative and quantitative analysis. So the fact that each element absorbs and emits its own unique wavelength means that when we're going through and doing atomic absorption spectroscopy, we don't have any interference from other atoms when we're trying to determine how much of something there is. Okay, so what that means is that if we're trying to determine if there's copper present, okay, we will use something called a copper cathode lamp, a hollow cathode lamp of copper. Right, that's a mouthful, sorry, and because that copper that we're using is emitting light that only copper will absorb, if we've got zinc or magnesium or any other metals in there, they won't interfere. So what we do is we create a calibration graph from some standard solutions, okay, and we then work out what our absorption is and determine therefore what our overall concentration will be. Again, I'm not going to go through this in too much depth because over here is a YouTube video, which is one I strongly recommend you have a look at, which goes through all the setup of the apparatus for atomic absorption spectroscopy and shows how we plot calibration graphs, how we use the value of absorbance to get our final concentration, and it's quite in depth, so I really recommend you look at that. So that's the end of this first topic for monitoring the environment. As always, if you've got any questions, just ask. Hopefully it's made sense, and yeah, practice the questions from the weekly exercises and you'll be fine. Thanks, guys.